Okay, so welcome everybody to the coding theory session. So the first talk is going to be given by Fernando, and it's going to be about unique decoding. So let's go.
Thanks, Yuval. I'm going to talk about unique decoding of explicit epsilon balance codes near the Gilbert-Varshimov bound. This is joint work with Dylan Quintana, Shashank Srivastava, and Madhur Tusiani. And the goal of the talk is going to be to present a new unique decoding algorithm for Tashma's codes, which are going to introduce shortly. And the binary code is very simple. It's just a collection of binary strings. Here you're representing by black boxes the elements of the code, namely the code words. And here we have our space f2 to the n. And you have two fundamental parameters, the distance of the code, which is going to be normalized here, and also the rate, which is the fraction of information symbols. And we have a well-known tension between the rate and the distance. The higher the rate, typically the lower the distance, and vice versa. And in the picture, here is a lower rate code, and you can achieve larger distance. And here, if you try to pack more code words, then the distance becomes smaller. And the natural question is, what is the best trade-off between rate and distance? And in the 50s, Gilbert and Varshimov, they established some non-constructive existential results. So they defined this curve here, below which codes exist, although we may not know how to explicitly construct them. So everything here is existential. There are codes. And a little bit above, McAllis and all, they show that there can't be codes achieving better parameters here. So this is a plot of rate versus distance. And in this talk, we're going to focus on this particular regime of distance half minus epsilon. And why do you care about the GV bound? Because it's nearly optimal. And for this distance, what we have by the GV bound is a rate that's epsilon squared. And by McAllis et al., we could do only a log 1 over epsilon factor, if possible at all. So in this sense, the GV bound is nearly optimal. Okay. And it took many years for an explicit construction to emerge, and Tashma had this beautiful result using expander graphs. And he achieves codes of the desired distance, and the rate is nearly optimal. So here we have an exponent of 2 plus a little o term, and this little o is going to 0 as epsilon goes to 0. So it is an amazing result. And one question was left open in that work, namely if those codes were efficiently decodable. And in our work, we show that the answer is yes. Tashma's codes, they are efficiently unique decodable. And more precisely, our main result is as follows. So there are Tashma's codes that achieving the correct distance, the correct rate. This beta is the little term that we saw before. And the running time is capital N raised to some, there is some exponent here that depends on epsilon and beta. And capital N is the block length. And the factors here, the hidden factors, they are polynomial in epsilon and beta. And moreover, if you're willing to trade the quality of this beta, if you're interested only in arbitrarily small, but we fix this beta, then we can make the running time no longer depend on epsilon in the exponent. It becomes fixed polynomial time. So that's our main result. It's a unique decoding result for Tashma's codes. Okay. And efficient unique decoders near the GV bound or at the GV bound, they were known before, but those results, they were for non-explicit codes. So Tashma's codes, they were the first explicit near the GV bound. And now let's move towards Tashma's codes. And they are going to be based on this interaction of expander graphs and codes. So you're going to use the pseudo-random properties of an expander graph to boost the distance. So that's what happens in Tashma's construction. And let's take a concrete example here. You're going to take a bipartite graph with any vertices here on the left and a bunch of vertices here on the right. And you're going to take an arbitrary word, and you're going to identify each symbol of this word with a vertex here. And on the right, what you're going to do, you're going to look at the neighbors that we have here, and you're going to take the XOR of the corresponding symbols. So this is going to be a way of amplifying the distance of the code. But when you do that, we are going to also lose the rate. The starting block length of the code was n, and now the final block length is the size of w. So we have a rate loss. And it's important that the amplification is worth this price of this rate loss. Okay, and this was proposed initially by these authors. And more formally, what is a direct sum? So you take any word, you take any collection of tuples, and you're going to form a new word such that it's going to be indexed by tuples. And for each such tuple, you take the XOR of the corresponding positions, and you call this sum. That's going to be our notation. And the important quantity here is the bias, which is the difference between zeros and ones. And you're going to work in this normalized fashion. And a very useful object was a paired sampler. When a collection of tuple is able to take a word of a given potentially large bias to a much smaller bias when you take the direct sum using this collection. So this is called a paired sampler. And an important question is how to build those paired samplers. And Tashma showed that if you take an expanded graph and you choose very carefully a sub-collection of FOCS, then this is going to be an amazing solution. You can get direct sum codes achieving your optimal parameters. So it's a carefully chosen sub-collection of FOCS on the sparse expander. But we are interested in the coding and what the coding direct sum looks like. And let's start with the setting that we have a base code of a small distance, you have a collection of tuples, and then you form a direct sum code, and this is going to have large distance by construction. So that's our setting. And let's see what unique decoding looks like. So we have a pristine code word, y star, and it gets corrupted to some y tilde. And now we have this y tilde at hand, and you'd like to decode. So we are looking for a z in the base code such that when you compute parities here on the right, it agrees as much as possible with those right-hand sides that are given by y tilde. So you're looking at some form of k XOR instance, right? So you want to find the z such that when you compute the pairs on the right, it agrees as much as possible. So more formally is this optimization problem. So instead of being a vanilla k XOR, you are looking at some guy in the base code. But it may be hard to find a guy in the base code directly. So we are going to relax that and say that we are interested in any word in the base code as long as it's nearly optimal for this CSV. And once you have that, there is this lemma that you're not going to prove, but if the paired sampler is strong enough, if the collection of tuples is a strong enough paired sampler, then this approximate nearly optimal solution is going to lie in the unique decoding ball of the corresponding z star. So z star is such that it lifts to y star. And then once you have this z tilde with this guarantee, you can invoke the unique decoder and finish the job. So the moral here is that it's enough to find any nearly optimal solution and use the unique decoder to self-correct the remaining errors. And why you can solve k XOR in this case is because we have a collection of expanding tuples. And we can use the sum of squares hierarchy, the SOS hierarchy, to approximate KCSP's, more precisely k XORs there. And what are our techniques to decode Tashma's codes? I'm going to describe them only at a very high level. The first thing, we have this CSP algorithm based on SOS, and you try to decode Tashma. And several parameters they are going to raise. And unfortunately, it doesn't yield near optimal rates. And now, in our previous work, we also had a least decoding machinery, and you're going to do least decoding to perform unique decoding. And somehow, some of the parameters they get better with this. It's like killing a fly with a bazooka, but somehow things are better. But still, the rate is not quite good. We have a rate that's quasi polynomial, not even polynomial at this point. So we still need an extra idea. And the extra idea is going to be a form of recursion. So we call this recursion code cascading. So Tashma's walk collection, it admits a form of recursive structure that allows us, instead of forming the direct sum of a base code all the way to the code of right distance, we are going to do this incrementally. We take here and form a direct sum. And then we'll take here and form another direct sum, and here another direct sum, and so on. But why is this useful? Is because when you're going to do the coding, when you decode the code here, you're going to invoke the unique decoder in the subsequent level. And the parameters, they behave in a much nicer way. So that's how we can achieve nearly optimal parameters. So with least decoding via SOS and this recursive structure, we can indeed perform unique decoding of Tashma's codes. Okay, so that's all that I had to say. Thank you very much for your attention, and please let me know if you have questions.
Okay, so let's thank the speaker. And please, questions. Okay, so one thing which was a bit bothering me, so it seems because all of the hocus pocus that you're doing, that the algorithms are not going to be very practically efficient. Do you think that there's any hope for something which is usable in practice?
I think yes, but it should require some work. So our result is based on the SOS hierarchy, and it's known that SOS is very slow, right? Typically, it's not the fastest algorithm, and we hope yes that there might be faster algorithms, but to make the whole scheme efficient in practice, then I think even the constants, they need to be good, right? So everything needs to be good to be, but I think that there is still a lot of progress to be made towards a real practical unique decoder. That's a good question.
Okay, so you're hopeful.
I can add to that if, I mean, so in some follow-up work, we think now we can get sort of near linear time algorithms for these. I mean, whether these are practical or not is still up for debate, I suppose, sort of what the constants are and so on and so forth. But the exponent of n in the polynomial is 1, so it's nicer than what SOS gives.
Sure. Okay, so that's definitely more practical. If that's anything.
Yes,
or less impractical, but yes.
With SOS, it's definitely a proof of concept. It's not practical at all, right? The exponent it's huge.
Okay, more questions.
Sure. Sorry, can I ask a question then? Do you think that there is any hope that you could do some sort of local decoding of these codes, or like you think their structure would admit such a local procedure?
I would hope so. We haven't tried, but I would hope so. I would hope so that there might be some hope of local decoding. And that there are codes near the DGV bound, non-explicit, that are locally decodable. So I think it would be interesting to look at them and see what these techniques can say there. But I haven't tried, so I don't know. But yeah.
Cool. Thank you.
You're welcome.
Any more questions? Okay, so if not, let's say thank the speaker again. Long step for everybody. And great, so Argument, you can set up your next your slides.
Sure.
But we'll still have a couple of minutes, so either I can like do a short stand-up routine, just in case people hop from session to session, or we can let Raghavan start. What do you think?
I think we should start at the right time because people may be planning on that.
Excellent. Yeah, but I think I'll skip the routine anyway. Yeah, well, I haven't practiced, you know. Some people would prefer to do stand-up anyway. I was always very bad at telling jokes. But if somebody else, you know, wants, we have like 2 minutes. If you always wanted to, you know, crack up some jokes, this is your chance. Your 2 minutes of fame, 1 minute of fame.
I don't know if I have any jokes, but actually I thought of another question if we still have some time.
Yeah.
So it was mentioned, I guess this was actually mentioned by Madhur, that you now have sort of a new approach to get linear time decoding that doesn't use SOS. Is it possible to say a word or two about how that decoding algorithm goes, or is it too complicated to explain quickly?
Let Fernando answer.
It doesn't use SOS, but it still uses an SDP. But it's a much simpler SDP now. And the key idea is that you're going to do some sort of weak regularity decoding. So like in freeze canon. So in SOS, it's what we did. We gave the problem to SOS, and SOS did its magic. And here now you're inspecting the structure of the problem. So you have those expanding tuples somehow. And we can decompose them in some sort of weak regularity decomposition in the style of freeze and canon. And we can do this very fast. And that's the key component towards a near linear time decoder there.
Oh, interesting. Okay, cool. Thank you.
Sure.
Okay, so thanks again. And now we're going to hear Raghuvansh, and he's going to talk about interactive coding and the relation to tree codes, other relations to tree codes. Yeah, go ahead.
Thank you. This is a talk on interactive coding, and I'll tell you about a new approach to get interactive coding schemes that are both deterministic and efficient. This talk is roughly structured as follows. I will first describe interactive codes. I will define them as a generalization of one-way codes that you heard about in the last talk. I'll state our main result and put it in context. And if I have time, I'll have this third section, which has some of our techniques, and I'll go over these. So let's start. What are one-way error correcting codes? These are codes that are studied in the two-party message transmission setting. You have two parties, Alice and Bob, and Alice wants to send a message M to Bob. Now, this task is non-trivial for Alice because the channel connecting Alice and Bob is noisy. And if Alice sends a message M, then some small adversarial fraction of the bits will be corrupted, and Bob will receive a message M prime different from M. To fix this, Alice, therefore, will first encode her message M to get a code word C. She will send the code word C over the channel. This will be corrupted by the channel, so Bob will receive a code word C prime. Even though C prime is different from C, it still has enough information because we use a good error correcting code to allow Bob to decode M from it. Okay, so what do we mean by good error correcting code? Well, ideally, we would like the code to be deterministic, which means that Alice's algorithm here and Bob's algorithm here are both deterministic. They're also efficient, which is polynomial time in the length of the input. And we also want the code to have constant rate. So by that, I mean that the length of the code word C is only a constant factor more than the length of the message M. And this corresponds to the communication overhead of noise. And we want that overhead to be only a constant. We have codes with all these three properties, so we can send one message M over a noisy channel. But now let us consider how about running a protocol over a noisy channel where there are many messages, each message dependent on all the previous messages over in either direction over the noisy channel. This is also something we know how to solve. And this can be solved in actually two different approaches broadly. The first approach uses the fact that if Alice somehow knew all the messages she was going to send over the channel beforehand, she does not know that because her second message, for example, depends on the message she receives from Bob here. But if she knew all her messages beforehand, then she could just take all of these messages, encode them using an error correcting code, and send the encoding. And the same for Bob. And therefore, if Alice and Bob both knew the entire set of messages that they're sending, then this task was just two instances of the one-way task. However, they do not, and these messages are revealed to them online. And therefore, in order to solve this task, it will be ideal if we have an error correcting code that is also a commutative of this online property. Such codes are defined and they exist. These are called tree codes. However, all known constructions of tree codes are inefficient. So any interactive code that is that derives from this approach is deterministic, but it's not efficient because to date, we do not have efficient constructions of tree codes. The other paradigm of interactive coding uses the fact that Alice and Bob in an interactive setting can detect errors that the channel inserted. How will they do that? Well, Alice has a set of messages that she sent over the channel, and Bob has a set of messages he received from Alice over the channel. If there were some errors in this channel, then the string Alice has or the transcript Alice has and the transcript Bob has will be different. And therefore, to detect the channel errors, it is sufficient to just check if the string or the transcript Alice has sent over the channel is the same as the transcript Bob has received from the channel. This can be done by standard hash functions. And because we are using hash functions, a code based on these lines will be randomized, but it will be efficient because hash functions are something we know efficient constructions of. So we have two paradigms for interactive codes. One is deterministic and inefficient. One is randomized and efficient. And the question we consider in this paper is whether it is possible to get codes that are both deterministic and efficient at the same time. based on these two approaches, there are actually two approaches you can take for this question itself. The first approach is, can we have tree toads that are efficient? And the second approach is, can we de-randomize the hash functions in schemes that use them? So let's go over these approaches one by one. The first one is, can we construct tree toads that are efficiently encodable and decodable? Because you need both to run an interactive code. And this question has been studied almost since the same time the first interactive code was studied. And the first tree toad that was shown had a constant slowdown. So this is ideal. And although it was neither efficiently encodable nor efficiently decodable. So this is something that will not allow us to get interactive codes that are efficient. Then in 2014, we had a new construction that was efficiently encodable, still not efficiently decodable. And also its correctness relied on a conjecture that we do not know how to show to date. So if this conjecture holds, then we have a tree toad that is efficiently encodable. I emphasize this does not imply an interactive toad because we need efficient decodability, but this does give a tree toad that is efficiently encodable. Very recently, we actually have provably a tree toad that is efficiently encodable, but not efficiently decodable. But this one has a slowdown of slightly super constant. Its slowdown is log n, where n you should think of as the length of the protocol. So it's like doubly logarithmic in the length of the protocol. It's not ideal, but it's not too bad. And again, this tree toad is not enough for interactive codes because, again, it's not efficiently decodable. And the conclusion from this slide is, yes, we are making progress, but it seems that efficient encodability is a much easier question for tree toads as compared to efficient decodability. We may, in near future, get a tree toad that is constant slowdown and efficiently encodable, but efficient decodability is much harder because we do not even have a candidate construction that is efficiently decodable. This is where this approach is currently. The other approach is to de-randomize, is to take a randomized interactive code, for example, from these two words, say BK12, and de-randomize it, replace the hash functions in the interactive code with something deterministic. And this is the approach we take. We show that this can actually be done. And this brings me to our main result, which is, if you have efficiently encodable tree codes, I do not assume efficient decodability. I de-randomize the code. I de-randomize the hash functions using only efficiently encodable tree codes. If you have such tree codes, then you can use them to de-randomize the hash function-based interactive coding schemes and get a deterministic and efficient interactive code. Now, this is a reduction, and applying this reduction on known codes, we actually get new schemes. For example, this is the code I told you about, the code that was efficiently encodable, not efficiently decodable, but had a log in slowdown. This plugging into our theorem will give you a deterministic and efficient code with the same slowdown. And this is actually the best slowdown known to date for a code that is deterministic and efficient. Also, we have this, there's an asterisk here because the parameters are slightly different, but the ideas do extend. We have this tree code that is constant slowdown, but under a conjecture, also efficiently encodable. And if you plug this into a reduction, then you get an interactive code that is actually ideal. You get something that's deterministic, efficient, and constant slowdown under the same conjecture. Okay, so that is the results. And now I have, I think, 1 minute. So I will try to cover whatever I can, but I'll maybe stop at some point and just take questions. So let's see, what is a tree toad? Now I want to give you a technique. So I'm going to tell you how we replace hash functions with tree toads. And for that, a tree toad is just a binary tree that is, say, infinite, and every edge is labeled by a symbol from some alphabet. These symbols satisfy a distance property. So if you have two different leaves, then the symbols on the path to the two leaves will differ by and then in the large fraction of the locations. So say 0.9 of the locations on this path will be different for both the 0.9 fraction of the symbols on the path will be different for both the leaves. And intuitively, the reason we can replace these tree toads, hash functions by tree toads, is because this is sounding very similar to a hash function. as long as you were on the same path, the tree toad always agrees. You always have the same symbol. And when you start deviating, then just like a hash function, 0.9 of the locations where you deviate, you get different encodings. And it seems like we can substitute these directly into the protocol and get something deterministic, but that's not the case. Because when you have a hash function, then for any two pairs of strings that are different, the hash function will be different with high probability. And the important part is that it holds for any two pairs. Here we do have tree toad symbols that are different, but that only works for 0.9 fraction of the strings that are different. This means that there is a small 0.1 fraction of the tree toad where even though you're in different locations, you will not be able to detect this. And actually, most of our ideas go into how to get outside this. We call these unprotected regions in the tree toad and get and finish the reduction to get an interactive code. So I won't go into any of the ideas. I think I covered many of them in the long talk, so please refer to that. They are really cool ideas. And with that, I'll stop speaking. Thank you.
Okay, so let's thank the speaker. Okay, any questions? Don't be shy. So why do we care about deterministic protocols?
Why do we care about? Well, there's a theoretical interest that if you want, for example, just like in the last talk, we have error correcting toads that are deterministic, they are efficient, they have the ideal rate distance trade-off. We would like to get the same thing for an interactive code. We like an interactive code to be like deterministic, efficiently computable, even the ideal rate distance trade-off, which is the topic of my next talk actually, and all those nice things. And this is one step towards getting that.
Okay, and another question. So here you show how tree codes can function as hashes. Do you think you can go the other way around?
Hashes as tree toads. So we do know that if you just take this tree that we have here and you assign these labels randomly, uniformly randomly, then you get an object which is slightly weaker. It's not a potent tree toad. It is not quite a tree toad, but it is still strong enough to imply an interactive coding scheme. So hashes do give you something like that. A hash, even a random function is a hash. So if you label them randomly, you get a hash and you get a potent tree toad. So I think hashes can give you something like that. But a tree toad is harder because in particular, if you label these things randomly, then you do not get a tree toad. And that can be shown. To show that a tree toad exists, you need like sophisticated arguments on the structure of these nodes. And it is actually a very clever construction. So yeah, I don't think it will imply it as is, but it will give interactive codes because it implies potent tree codes.
Okay, so there's a question in the chat from Benny Applebaum. So can't you get efficient decoding using concatenation? Losing a bit in the rate?
Efficient decoding for the tree toad? I think that's what it's meant. I actually, so let's see, how should I say this? I think that it's my intuition, I'm not sure how correct this is, but I think that decoding tree toads is sort of, it's very different from decoding like standard error correcting toads. I'm not sure how many of the ideas do extend, but yeah, I haven't like really looked into the details here. I cannot answer that like very specifically.
Okay. Okay, so let's thank Agumbanch again. And we'll get to hear more of Agumbanch in 2 talks, so we'll get more of him. So don't worry, if you have more questions, you'll get to ask them. So can you please
Sure.
answer? And Jonathan, you can share yours. Thanks. I might be the only person in the universe who knows how to pronounce the surname. I think it's Mosheov, right?
Wow. Yeah.
Because last time I corrected me, so.
Yeah. Nice.
Okay, so I see started screen sharing, but I don't see anything being shared. Just
Oh, wait, it's paused.
black. Yeah.
Yeah. Is this okay now?
Yeah. Oh, that's much better.
Okay, cool. Okay.
Okay, so the next question by Yonatan Moshev about LDBC codes.
Okay. Okay, thanks. Yeah, so I'll be talking about list decoding of LDPC codes. And this is a joint work with Nick Resch, Nogel and Tzvi, Shashwat Silas, and Mary Wooders. Okay, so let's once again start by quickly going over some basics of codes. So a Curie code in our case is just a subset of FQ to the N. And let's review again how code is usually used. So in a classic setting, Alice and Bob want to communicate from afar, obviously because they need to keep social distancing, over some noisy channel. So the blue dots here are the code words, and Alice is going to send Bob a message X from the code, but due to noise, Bob receives some noisy version of X. But assuming that the amount of noise isn't too large, Bob can then search for a code word near the word that he received, and he manages to recover X back, and that's basically how codes help us do error correction. Next, I want to define the rate of the code. So this is just log the size of the code over n, and generally we like the rate to be as large as possible because that allows for more efficient communication. And finally, throughout, we're going to assume that q, the alphabet size of the code, is constant, while n always goes to infinity. Okay. Next, let's talk about our noise model. So our noise model is adversarial noise of some fixed ratio p. So that means that suppose that Alice is sending a message X to Bob, then some adversary is allowed to choose a p portion of the symbols in X and just change them as we please. Now, if despite all the noise, Bob can always correctly recover the message X, then we say that this code is uniquely decodable. And combinatorially, the equivalent condition to being uniquely decodable is that every radius p Hamming ball in FQ to the N should contain at most one code word. So now this leads to a natural relaxation, which is called list decoding. So suppose that now, instead of allowing every ball to contain at most one code word, we allow every p ball to contain at most L code words, where L is some either a constant or some small number that's allowed to be, say, polynomial in N, but no more than that. Then the code is said to be PL list decodable. And while list decoding means that Bob cannot necessarily uniquely recover the message X, he can still produce a small list of possible messages that Alice might have been trying to send him. And list decoding has strong motivations. It has many classical applications, and it has been studied for a long time now. Okay, so a natural question about list decoding is, do there exist interesting list decodable codes, and what are the possible rates? So let's review what's known. So if we're just interested in this question from a strictly combinatorial sense, then you can say that we pretty much know everything. And what do I mean by that? So let h of p stand for the Curie entropy function. So 1 minus h of p is called the channel capacity. And there's a classic theorem that says that there exist list decodable codes of any rate up to the capacity, and there are no list decodable codes with rate above capacity. So basically, this theorem just completely pinpoints the optimal rate for list decoding. And in particular, it's going to be important that this theorem is satisfied if we just take a random linear code. So a random linear code is just you just sample uniformly a random linear subspace of FQ to the N, whose dimension is Rn. And if we take that as the code and R is less than capacity, then the theorem says that random linear code is likely to be list decodable for some small L. Okay, but of course, it can seem like everything is known because we know the optimal rate, but of course, it's not that easy. A more complicated question would be not just which codes are list decodable in the combinatorial sense, but which codes actually admit an efficient list decoding algorithm to go with the combinatorial property. So what do I mean by a list decoding algorithm? So consider in the Alice-Bob communication scenario, consider the job of Bob. So he's given some noisy word Z, and he needs to compile a list of all the possible messages that Alice might have been trying to send him. And in other words, he needs to find all the words in the code that are of Hamming distance at most p from the word Z that he received. And the combinatorial theorem guarantees that there are codes where only a small number of possible words there can only be a small number of words that are that close to Z. But it doesn't tell us what Bob needs to actually do in order to find these words. So what we're looking for is a code that's both combinatorially list decodable up to capacity, but is also equipped with an efficient algorithm for Bob that, given Z, finds the list of code words that are close to it. Now, the state-of-the-art are codes such as, say, folded Reed-Solomon codes that can be list decoded in polynomial, but still superlinear time. And the holy grail here would be to find a code that's list decodable up to capacity in linear time. Now, in this work, we're trying to advance on solving this problem. So specifically, our hope is that linear time list decoding can be achieved by a certain family of codes that are called LDPC codes. So what's an LDPC code? So a linear code is called said to be LDPC if it is defined by a set of sparse linear constraints. So for example, suppose that, as in the example here, every linear constraint involves at most 3 code variables. Then we say that the code is a 3 LDPC code. Now, LDPC codes are known to have many desirable properties, and one of them is that some LDPC codes actually admit a linear time algorithm for unique decoding. And in fact, it also goes the other way, that the only codes for which we know any linear time unique decoding algorithm are all in the LDPC family. Now, the thing is that unique decoding is just a special case of list decoding. Unique decoding is list decoding with list size 1. So when you're looking for codes that can be list decoded in linear time, it makes sense to focus on codes that you already know how to do unique decoding for in linear time. And for this reason, LDPC codes look very promising. But the catch here is that you want to list decode up to capacity. And until the work I'm presenting now, it wasn't even known whether any LDPC code is combinatorially list decodable beyond any trivial bounds. And this is a necessary condition for what we're trying to achieve here. In order to have an efficient algorithm for list decoding up to capacity, you first just need combinatorially to be list decodable up to capacity. And this is where our main result comes in. So we're going to show that a certain natural, very important family of LDPC codes is indeed list decodable up to capacity in the combinatorial sense. And we see this result as maybe a first step towards actually having an algorithm. Okay, so now we can actually state our main result. For context, it's best that we present it next to this theorem of Gallagher from '62. So Gallagher proved that in the combinatorial sense, random LDPC codes from a certain ensemble of random LDPC codes called the Gallagher ensemble, they achieve unique decoding with rate up to 1 minus h of 2p. And this is known as achieving the GV bound. And it generally means that LDPC codes perform just as well as random linear codes for unique decoding. And more precisely, the theorem says that you approach this bound as you increase the sparsity parameter of the LDPC code. You approach it very quickly. Now, our main result is just saying the same thing, but for list decoding rather than unique decoding. So we're saying that random LDPC codes are also list decodable combinatorially up to the capacity rate, just like random linear codes. So this is our result. Let's talk a bit about our proof. So in order to discuss our proof, I want to first talk about what it means for codes to actually be list decodable. So recall that we want a code that avoids having any p-ball in FQ to the n containing L+1 of the code words. So in other words, if there are L+1 words in FQ to the n that are all close to some joint center Z, we don't want it to be the case that all L+1 of these words are in the code. So such a tuple of code words that we don't want all of them to be in the code, we call it a bad tuple. And a code is list decodable if and only if it doesn't contain any bad tuple. And in the paper, we generalize this characterization of list decodability to a more general notion that we call a local property of the code. So informally, let B be any collection of tuples that you just don't want to appear in the code. okay, and subject to some certain symmetry conditions. And we say that a code satisfies the property PB if it does not contain any tuple from B. Then we say that a tuple defined like this, PB, is called a local property of codes. So for example, the characterization above shows that being PL list decodable is a local property. Now, the rest of the paper just deals with local properties in general rather than specifically list decodability. And the first step in our proof is actually a sub-theorem that's interesting in its own right. It has nothing to do with LDPC codes. It just talks about random linear codes and local properties. And what it says is that local properties have sharp thresholds for random linear codes. And by that we mean the following: let P be some local property, and plot the probability that a random linear code of rate R satisfies P. So here in this plot, R is the x-axis and the probability is the y-axis. And there is the theorem says that there is some threshold rate such that up to this threshold rate, the probability that the code satisfies P is very close to 1. And then it rapidly drops and becomes very close to 0. This is called the threshold phenomenon. And we actually compute this threshold, RP. And just before moving on, I'll say that this theorem is actually being used recently by itself in other applications in recent papers. And finally, this allows us to, using this theorem, we can prove the main theorem via a reduction from LDPC codes to random linear codes. And what this reduction says is that just take any local property. If for some rate R, the property holds for random linear codes with high probability, then it's also going to hold for LDPC codes with high probability. And this allows us to infer the main theorem about list decoding because we know that list decodability is a local property. And we know from previous works that random linear codes are list decodable up to capacity. And now this reduction says that any local property that holds for random linear codes with high probability also holds for LDPC codes with high probability. That's it. I'll just finish by stating two open problems. One is that we really want to further develop this theory of thresholds for random linear codes, or in general for random codes, and connect it to other random objects for which we have a very developed theory of properties and thresholds, for example, random graphs. And two, I'll just recall the motivating question, which is finding linear time list decodable capacity achieving codes. And that's it. Thank you very much.
Okay, so let's thank the speaker. So we already had one question, which is what do you mean by random code? But it's just, we take a random generating matrix, I guess, or random parity check matrix, whatever you prefer. Any questions?
Here I see there's another one. Can you relate list decodability to the expansion properties of underlying graphs or to some combinatorial property of the underlying code? So I guess the answer would be, let me think, I guess, Nick, if you want to correct me here, then feel free, but I think the answer would be that yes, but it's probably not optimal.
Yeah, I'd say something similar. Like usually when you use expansion type arguments to show your code has good distance, you're not going to achieve the GV bound and stuff like that. So I don't think expansion alone will be enough to explain why like a random code sampled from Gallagher's ensemble achieves list decoding capacity.
Mm-hmm. Yeah, I mean you might be able to show something, but it's not going to be optimal.
Mm-hmm.
Okay, so any more questions? Meanwhile, can you please stop sharing your screen so Argument can set up next time? Any more questions? So maybe a short question. So what you really show is a kind of de-randomization. Do you think you can de-randomize all the way and give an explicit statement?
That's a very good question. I don't know. I think like it's something we're thinking of, but I don't have a good answer. Yeah, that would be amazing.
Well, I hope you succeed. Okay, so last chance for a question. Well, we're out of time, so let's thank Jonathan again. And our next speaker, you already, next speaker, you already know them. This is Lagomanch again. And this time the topic is going to be interactive coding.
Yes, just like last time, this time the topic is interactive coding. But this time the focus will be getting codes with a binary alphabet, which means it can only send bits, and getting a high error resilience. The error resilience of a code is just the amount or the fraction of errors that you can decode from. So higher error resilience is good. And we would like to get error resilience larger than 1/8. And I'll explain in detail why 1/8 is so significant. So let's start with the definitions. These slides will look like the slides from the previous talk, but I'm not assuming that you remember any of that, and I'll redefine everything with a focus on the properties I need here. Again, I first want to define error resilience in a one-way setting where you have Alice and Bob, and Alice wants to send a message M to Bob. This time the channel can only send bits, so Alice's message is a bit string. And the reason she cannot just send the message is because there is noise. And more specifically, if Alice were to send the stay-bit message M directly over the channel, then an adversarially chosen theta fraction or theta k many bits of M will be corrupted. And Bob will get a message M prime different from M in theta k locations. Now, we want to still send the message M. And the solution is to use error correcting codes. We take the message M, encode it to a larger code word C from K to N. We send C over the channel. Theta fraction of the bits in C are corrupted. And this does not, because we use a good error correcting code, the fact that theta fraction of the bits in C were corrupted does not stop Bob from recovering M, and he can still decode. Okay, so basically the task of sending a message M over a theta noisy channel reduces to the task of constructing an error correcting code that allows decoding even after a theta fraction of the bits has been corrupted. And now let us ask the question, what is the largest value of theta for which there are such codes? It turns out there is a precise answer, and that answer happens to be 1/4. As long as theta is smaller than 1/4, there are codes that will allow you to decode in this way. And if theta is even slightly larger, then there's nothing Alice can do to send the message M to Bob. There will always be a set of theta and symbols that the adversary can corrupt, and Bob will not be able to decode. Okay, so this was one message. Now let us go and generalize to the two message case where Alice and Bob both have messages, MA and MB respectively. And again, there's a channel that corrupts an adversarially chosen theta fraction of the symbols. And you want to exchange both these messages. I will call this the message exchange task. Alice wants to know MB and Bob wants to know MA. Now you could apply the solution from before in both directions. Alice can take MA, encode it, and send it over. Bob will decode. Then Bob can take MB, encode it, and send it over. Alice will decode, and they will receive both the messages. I claim that this generalization gives an error resilience of theta equals 1/8, so a factor of half lower. And this is because in order to fail this task, the adversary only needs to corrupt one of the two directions. For example, he may focus on corrupting the message from Alice to Bob. Then he will only need 1/4 of the messages from Alice to Bob, which is 1/8 of the total messages. And therefore, the error resilience is 1/8. Now, I took this message exchange task as a prototype for an interactive task. And it's actually the case because the message exchange task is complete. If he can exchange messages with some error resilience, he can also compute any function with the same error resilience. Why? Suppose you have a function f that you want to compute. You first exchange messages with some error resilience. Then once Alice and Bob have both the messages, they can compute the function privately and output it. So message exchange is complete for all interactive tasks, but there is an overhead. And the overhead is because when there was no noise, maybe Alice and Bob did not need to send the entire inputs to compute f. Maybe they could have done it in much cheaper. But when there's noise, this scheme will ask them to send the entire message, even for simple functions. So it's actually possible to avoid this overhead. And this was done by BR11. And they show that for all interactive tasks, you can get the error resilience of 1/8 with only a constant factor overhead. And this is ideal in all aspects, except that we do not know whether 1/8 is tight. We know that 1/4 is tied for one way, but we do not know whether 1/8 is tied for two way. And the open question after BR11 was, can we do better? In this paper, we show that yes, we can. And we show a binary interactive code with error resilience 5/39. This is larger than 1/8. And a quick way to see it is just seeing that 1/8 is 5/40 and 5/39 is larger than 5/40. Our scheme also has constant overhead, so we do not lose out on the overhead. We solved the open problem of BR11, and this was restated and emphasized in a lot of other works. But we do not solve it entirely. We do not have a constant above which there is interactive codes, below which there is no interactive codes. But we do narrow down the interval. Now we know that the interval is between 5/39, which is our result, and 1/6, which is EGH16. And finding this right constant is a great question that we leave open. Okay, but this is our main result. I will not describe the protocol that we have that gets 5/39, but I will describe in the remaining time why crossing 1/8 was so crucial. And this will be basically why 1/8 was a barrier that took so long to cross. And for that, let us again go back to the message exchange task. You have Alice and Bob, both of them have messages and inputs, and they are communicating over a noisy channel. I claim that this message exchange task has 3 properties, and each of these 3 properties corresponds to a factor of half in the error resilience. So binary alphabet will cost us a factor of half, unique decoding will cost us a factor of half, two-way task will cost us a factor of half. And let's see why. Well, by definition, this is a binary channel. So the codes you use are restricted to have a binary alphabet. And it is well known that when you have codes that have a binary alphabet, then the maximum distance that you can get is 1/2. This is as opposed to codes over a larger constant size alphabet where you can get distance 1. And this gap of 1/2 is the first factor of 1/2 here. The second factor of 1/2 comes from the fact that we require Alice and Bob to output each other's messages exactly. This is unique decoding as opposed to list decoding, which was the subject of last talk. And we also know that even in error correcting codes, if you require for list decoding, which is Alice can output a small list of values out of which one of them should be correct, then the error resilience that you can get is double that of unique decoding. This is true for the binary setting, this is true for the non-interactive binary setting, this is true for the non-interactive setting with constant alphabet, and so on. So this is the second factor of half. And the third factor of half is the fact that both Alice and Bob need to output. And in order to fail the task, you need to only corrupt one of the 2 directions. And this costs you a third factor of half because the length of the protocol is double now, and this will correspond to a factor of half overall. Okay, so you have these 3 requirements. Each of them correspond to a factor of half. But that does not mean that this is a barrier, because usually this happens, and usually you can combine 2 requirements and get something better. Here, the important thing is you cannot. If you talk about binary alphabet and unique decoding, but just a one-way task, then you get the error correcting code setting. And here we know 1/4 is tight. You cannot do better. If you combine unique decoding and two-way tasks without the binary alphabet, so now you have a larger constant size alphabet, you again have the fact that 1/4 is tight, and this was also shown in BR11. You can also take the third combination. You can combine binary alphabet and two-way tasks with without unique decoding. And even here, we know that 1/4 is tight, and this was shown in BE17. So regardless of which 2 properties you take, you cannot get anything better than the product of 2 halves. You always get 1/4. And this is really the barrier. There are 3 properties, and they all seem to be independent because you can combine them in pairs and you don't get any improvement. Our result basically shows that you combine all 3 together, you get an improvement. We are able to show that even though you cannot take pairs and get something, even if you cannot take pairs and get something, if you take all 3 of them together, then you get something greater than 1/8. And this is the great thing about our protocol. Next is a picture of our protocol that I won't talk about, but I'll refer you to the full version, and I'll stop here. Thank you.
Okay, so let's thank the speaker. Any questions? We have a lot of time for questions. And then maybe I'll start. So you're probably expecting this question. What do you think is the correct answer, like between 1/6 and what you get?
So we actually also considered this problem without the binary alphabet. Because we do not have one of these three, we do not have the binary alphabet, things are generally double. For example, here you had 1/4 for two-way tasks and unit decoding. And wait, sorry, maybe I'm not answering the right question. Okay, let me start again. The question was, what is the right number between 5/39 and
Right.
1/6?
More interesting question. You're happy to answer it also.
The question was, what is the right number between 5/39 and 1/6? And the answer is, I do not think 5/39 is tight. This is because we know that our protocol does not, like there are things that we can definitely improve on, but we don't go there because our focus was on getting something better than 1/8. I am not that sure, but I'm fairly confident that 1/6 can also be improved. So I think the answer lies in the middle, but I do not know the constant.
Because they don't have a guess.
No. We did this for the same problem without the binary alphabet, but with an adaptive channel. Everything here is non-adaptive. We did this without the binary alphabet, but with an adaptive channel. And there the answer was 5/16, and nobody expected this. Why would it be 5/16? It's not a nice number that you would expect. But yeah, it could be anything. It could be irrational for all I know.
Yes, so Max Hopkins asks, how do you get around some variable? But I think, so in your slides, you only had 2 messages, but I think the algorithm had more rounds.
Which one?
So there's a question in the chat.
Oh, I didn't see that. Let me see. Can you explain intuitively how Alice and Bob get around the adversary's nice strategy of corrupting more than 1/4 of the second message? So let me actually go to the protocol. Here, if you take the second message, then again, the length is 39n, 16 plus 20 plus 3, and the errors are 5/39, so the errors are 5n. The second message is actually trivial. You spend 20n, and because the corruption is less than 1/4, Alice can unity code. The magic in this paper happens in how the first message takes place. And that is broken into 2 parts. In the first part, you use unique decoding to get better error resilience. And in the second part, use the fact that the lists are small in size to get an improvement here. And here is our improvement. Here we are able to get around with 16 plus 3, 19 instead of 20. The second message is not where we get an improvement.
So if you only had 2 messages and you wouldn't get anything?
2 messages. This is actually 2 messages, right? Alice is sending something, Bob is sending something. After you encode them, you get more messages. But the non-noisy task was just 2 messages.
Okay, more questions? So I guess you also get improvements for any kind of alphabet size. I know in the limit it goes to 1/4, but probably.
Yes, that is true. I'm not exactly sure what the trade-off is. I don't know where it becomes better or worse. But like even if it's just 3, then I think the techniques can be applied, and you can get something better than what you would like naively get.
Okay, so I think like it converges faster to the limit, let's say.
Yeah. I didn't hear that, sorry.
I'm asking whether you think you get faster convergence to the limit in terms of the alphabet size.
Not that fast. I wouldn't expect it to be a super constant because step 3 is actually combining step 1 and step 3 is where we get the improvement. And this improvement was something so small that I don't expect it to change more than a constant if you increase the alphabet size slowly.
So there's another question in the chat about the list decodable code and what does it look like?
Oh no, I didn't say this. And this is actually like the main technical contribution of this paper. We are able to construct a list decodable code for interactive tasks. That was needed because you may not have message exchange. you may have a general interactive task and you want list decoding. We are able to get the list size all the way down to 3, which is super small. You usually want something that degrades as an epsilon or maybe like 1 over epsilon, but here our list size is 3, exactly 3. And we are able to get error resilience matching that what was known for one-way. For one-way, we know that you cannot list decode all the way down to 3 with error resilience better than 5 over 16. Here we get error resilience 5 over 32. So we lose a factor of 2, and we do not know if it is tight, but it at least matches what we know for one-way. We know that it's only a factor of half a way. So this is actually one of the reasons why I said this is probably not tight, because if you can improve for unit decoding, maybe you can improve for list decoding, and that will improve it overall.
Okay, so let's thank the speaker again. Can you please stop sharing your screen to let Ray share their screen? So Ray. Excellent. So the next talk is by Ray Lee, and it's about trace reconstruction.
Yeah, thanks for the introduction, Yuval, and thanks for having me. So yeah, I'll be talking about coded trace reconstruction in a constant number of traces, and this is joint work with Joshua Brackenseek and Bruce Spang. Okay, so trace reconstruction, or coded trace reconstruction, is motivated by DNA storage. So here's a simplified picture of DNA storage. You have some data, you write it to DNA, and then you read the data, and when you read the data, you get some noisy copies of your data, which we call traces, and from those traces, you want to recover your data. And we'll be dealing with this last step of recovering your data from the traces, and we'll deal with a particular instantiation called trace reconstruction. And we'll ignore the fact that DNA is four-area, we'll just pretend everything is binary. So the question for this talk is, how much does coding help with trace reconstruction? So maybe you're dealing with DNA storage, and instead of storing your data directly on DNA, you add some redundancy to your data to get something we call a code word. You store your code word in DNA, and you get traces of your code word, and you want to recover the code word from the traces. So the question is, how much does adding this redundancy help with trace reconstruction? And what I hope you'll see is that it helps quite a bit. Okay, so now I'll define everything for you formally. So first, I'll talk about coding, then I'll talk about trace reconstruction. So what is a code? A code is not a Python program. A code, as we've seen, is a set of strings. Here, so C here is a binary code of length n. The length of the string is the length of the code. We say elements of C are called code words. And the crucial parameter of a code we've already seen is the rate. It has this definition. It's always a number between 0 and 1. And in this talk, we're concerned with high rate codes, so codes of rate 1 minus epsilon, where epsilon is a constant. So just to give you some more intuition for what this means, one way to think about this is our code is size 2 to the n times 1 minus epsilon. Another way you could think about this is that there's a bijection between length n times 1 minus epsilon strings and our code. And this bijection is often called the encoding function. So in the application to DNA storage, this encoding function is exactly the step of we add redundancy to our data to get a code word. Okay, so that's all the coding theory jargon you need to know. Now, what is trace reconstruction? So trace reconstruction, the main object is something called the binary deletion channel. This has a parameter q, which is the deletion probability. And the binary deletion channel takes as input a string and outputs a string where every bit is deleted independently with the same probability q. And crucially, these are deletions and not erasures, so we do not know the positions of the deletions, and so we get a strictly shorter string. And this fact that we don't know the positions of the deletions makes this a particularly difficult thing to deal with and analyze. So trace reconstruction says you're given an unknown string and you send it through the binary deletion channel independently several times to get these traces, and from the traces you want to recover the unknown string. And typically the problem is formulated as how many traces do you need so that you can recover the unknown string with some reasonable probability, like 2/3. So we're trying to minimize the number of traces that we use. Now, if you were to come up with this problem formulate this problem yourself, you'd probably come up with what's known as worst case reconstruction. Here, you need to recover with probability, say, at least 2/3, no matter what the unknown string is. Another way to think about it is there's an adversary who looks at your algorithm, your reconstruction algorithm, and picks the worst case string, and you need to recover in that case with probability at least 2/3. There's also average case reconstruction, where the unknown string you assume is uniformly random from 0, 1 to the n. And in this case, you need to recover with high probability, not only over the randomness of the traces, but also over the randomness of the string. So this is an easier problem. And what we'll be dealing with is what we deal with is coded trace reconstruction. So here you design a code of rate 1 minus epsilon, such that if the unknown string is chosen adversarially from your code, you can still do trace reconstruction. You can still recover the unknown code word. And so this corresponds to this simplified DNA storage picture where instead of recovering an arbitrary string from traces, you're only recovering code words from traces. Okay, so some of you probably are familiar with the trace reconstruction problem. It's a very difficult problem, and so what's known about it? So for worst case reconstruction, there's a simple algorithm that only needs exponentially many traces. You just wait until you get a string with no deletions, and then you know your string. Less trivially, there's an upper bound that says you can do it in 2 to the cube root n traces. And very recently, this was improved when deletion probability is at most a half to 2 to the 5th root of n traces. And the best lower bound is polynomial in n. So there's this exponential type gap between the best upper and lower bounds for worst case trace reconstruction. For average case reconstruction, you can do much better than worst case reconstruction. You can solve it with sub-polynomially many traces to the cube root of log n, and the best lower bound is polynomial in log n. Okay, so now we can state our results. So I've listed again for you the best upper and lower bounds for worst case and average case reconstruction. I put them on a number line on the right. And so we're trying to so our question is, how much does coding help with trace reconstruction? So worst case reconstruction, you need exponentially many traces. And we show that for coded trace reconstruction, if you allow just rate 1 minus epsilon, then you can do a constant number of traces. So our upper bound is 2 to the cube root of log 1 over epsilon, and we get a lower bound that's log to the 5/2 1 over epsilon, roughly. So a couple of things to note. Indeed, this is a constant number of traces when epsilon is a constant. In fact, asymptotically, it's a pretty good constant. It's sub-polynomial in 1 over epsilon. Furthermore, this works for any deletion probability q. We also get polynomial in time encoding and decoding when epsilon is a constant. So polynomial time encoding means that encoding function that bijection from length n times 1 minus epsilon strings to your code words. This can be done, computed in polynomial time. And decoding means you can recover the unknown code word from your traces in polynomial time. So when the last thing is when the coded trace reconstruction problem was first formulated by Chiragchi, Gavris, Milenkovic, and Rivero, some constructions were given when epsilon is going to 0. Our constructions also work when epsilon is subconstant. And in these settings, we improve over the number of traces. There's an asterisk because the previous results get polynomial time encoding and decoding in all settings, and we don't get polynomial time encoding when epsilon is 1 over log n. Okay, so on this slide, you may notice that our upper and lower bounds look suspiciously like for coded trace reconstruction, looks suspiciously like the upper and lower bounds for average case reconstruction. And this is no coincidence because our results follow from a pair of black box results. So here, let T of n be the optimal number of traces for average case trace reconstruction on length n strings. So we prove the following pair of results. We prove first that there exists rate 1 minus epsilon codes using roughly T of 1 over epsilon traces. And furthermore, we prove a lower bound saying all codes of rate 1 minus epsilon need roughly T of square root 1 over epsilon traces. So now you take the upper and lower bounds for average case reconstruction, the upper and lower bounds for T of n, you plug them into these blue results, and then you get our results. Everything is T of poly 1 over epsilon, so you plug them in, and the logs just take the polynomial into a constant, so then you get our results. And furthermore, these not only give our results, but they say that any improvement to average case reconstruction gives an improvement to rate 1 minus epsilon coded trace reconstruction. So if the upper bound was somehow improved to 2 to the 5th root of log n, then we would get an upper bound. You automatically get an upper bound of 2 to the 5th root of log 1 over epsilon for coded trace reconstruction. And furthermore, notice that for the upper and lower bound black box results, they both involve T of polynomial 1 over epsilon. So that means that the reverse direction also holds, that if you improve average case coded trace reconstruction, that implies necessarily an improvement to rate 1 minus average case trace reconstruction. The line is a squiggly and the any is in quotes because there's these polynomial factors in log 1 over epsilon, and also the polynomials are not the same. So it's any improvement up to a polynomial. But essentially what this is saying is that our results are basically the best possible for coded trace reconstruction given our knowledge of average case reconstruction. Okay, so and then our last set of results is for large alphabet trace reconstruction. So you can define coded trace reconstruction over large alphabets. You can define the deletion channel over large alphabets. You can define codes over large alphabets. And what we show is that in this setting, there exists constant rate codes with a constant size alphabet that use log1/epsilon traces, and this is optimal. And there's a couple of nice things. We get the right dependence on Q. We show that large alphabet coded trace reconstruction is strictly easier than binary, and this, to our knowledge, is one of the few tight results for trace reconstruction over the deletion channel. Okay, so I won't say anything about our techniques. You can watch the full version of the talk for this, but some open questions. Obviously, there's this exponential type gap for all of worst case, average case, and coded trace reconstruction. You could try to close this gap. And as we saw for average case and coded trace reconstruction, these are sort of the same problem by our results. There's also giving practical trace reconstruction for DNA storage. The constants in our results are very large. We hope the ideas can be applied, but yeah, it'd be interesting to get trace reconstruction codes for trace reconstruction for, say, smaller values of n, or error models that are more realistic to DNA. Okay, so now I'll wrap up. So we started by motivating coded trace reconstruction by DNA storage. We talked about what's known about it. It's a difficult problem. Then we showed that you can do coded trace reconstruction in a constant number of traces. So does coding help with trace reconstruction? Yes, it does. You go from exponential to a constant. We showed this equivalence between coded trace reconstruction and average case reconstruction. And we showed that log1/epsilon traces are optimal for large alphabets. Okay, that's it. Thanks.
Okay, cool. Let's thank the speaker. Okay, any questions? Maybe I can start off. Are there any least coding versions of all of this?
That's a good question. I don't think we considered that, and I'm not sure.
Yeah, I have to say I had a lot of questions throughout the talk, but basically you answered all of them in subsequent slides. So. Yes, so you said that for large alphabets you get much better. But do you think that, let's say, an alphabet of size 4 will be actually better than an alphabet of size 2?
Yeah, that's a good question. So we get an improvement over binary for large constant alphabets, but do we get an improvement for alphabet size 4? I don't know. So the alphabet size that we need for our large alphabet construction is something that depends on epsilon. So it's like exponential in 1/epsilon. And so yeah, you need the alphabet size to be somewhat large. And so I'm not sure what that says about 4. Maybe it's the improvement is not. If there is an improvement, maybe it wouldn't be as substantial. I'm not sure.
Okay, so another open question would be to improve the dependence on epsilon on the alphabet size.
Yeah, that's right.
Do you have a guess, like how big the alphabet has to be?
I don't know. Yeah. I think, yeah, if you could get, alphabet size polynomial 1/epsilon, that would be very interesting. I'm not sure if that is possible.
Okay, there's a question in the chat. So how much of your techniques can work in stronger error models? Like what models do you have in mind, Paul?
So some of the models from the last slide. So for example, if you had in duplications or I don't know that substitutions would be so different from insertions, but
yeah. Yeah, so sort of, okay, yeah, that's a good question. So how much do the techniques work in these other models? So basically what we do is we start with our large alphabet construction, which involves some error correcting codes and synchronization strings, and then we concatenate it. We do this careful code concatenation where there's a binary code underneath. And so I think if you could get, binary codes that do handle average case trace reconstruction for these other error models, then my guess is you could turn them into binary codes for coded trace reconstruction in the same way that we do. And my guess is you could probably also, and maybe you could get similar results with worse guarantees just naively without better average case reconstruction. But that's sort of what's going on, that we do some code concatenation. And so if the code underneath can handle these, then our code might be able to handle them.
Thanks.
Okay, so let's thank the speaker again. And again, can you please enter your screen?
Oh.
So that David can set up. Oh, that was fast. So now you just need to see its full screen. Excellent. Okay, so the last talk in this session is going to be given by David Weitz about network coding. David? We can't hear you. Okay, we still can't hear you. Yeah, so some technical problems. Well, if anybody, in the meanwhile, has any questions to anybody else who gave talks.
All right, can you guys hear me now?
Yeah.
Perfect. Okay, let's do this. Can I share screen though?
Hopefully.
Yes. Okay, good. So sorry about that little hiccup. Let's see. Good. So where were we? Right. So as I was saying, my name is David Weitz, and in this next 10 minutes or so, I'd like to tell you about joint work with Bernard Heupler and Goran Žužić, titled Network Coding Gaps for Completion Times of Multiple Unicasts. And as you could guess from the rest of the talks in this session, the reason this talk is in this session is this circled word here. But as you'll see, the model is quite different from most of what we've seen before, less Alice and Bob, more communication between numerous agents in a network. And hopefully all of that will be clear shortly, and also hopefully I'll also convince you that there's some interesting questions here for coding theorists and theorists more broadly. Okay, so let's start with some motivation. So consider your favorite communication network, the internet, which is nothing but a number of computers all interconnected by a sequence of routers. And now consider the most basic communication primitive, point-to-point communication. For example, Yuval might want to send me a quick email asking me if my internet connection is fine or what the hell is going on with this the audio on my talk. Okay, so this kind of problem is referred to in the literature as a unicast session, where uni refers to the fact that there's a unique recipient, and cast is in allusion to the broadcast problem. Okay, so a simple enough problem. We can simplify it further by abstracting away all these pretty pictures. And what we're left with is just an undirected graph with two distinguished nodes, sender and receiver. And what we'd like to do is find some path along which to send a message from the sender to the receiver. Now, the particular message we were talking about earlier is quite time sensitive. You would like me to respond as quickly as possible. So naturally, we'd like to send along a shortest possible path, which corresponds to a fastest possible communication. So instead of going along the roundabout path, we'll send along the direct path. Okay, so single unicast is somewhat simple. We all know how to compute point-to-point shortest path. What happens if we have a number of unicast sessions in parallel? So let's say here we have the blue session and the red session. So again, we'd like to send along the shortest possible path, but unfortunately here we run into an issue, which is bandwidth bottleneck. So in particular, we cannot send more than a certain number of bits of information per second along each edge. So maybe we can't send along these two shortest paths simultaneously, because we can't send both the red and the blue message at the same time. And these kind of challenges are what this talk deals with. How should we perform multiple unicasts in parallel? So to be a bit more concrete, what is the model? So a k-unicast instance consists of an undirected graph. This is the communication network, and k source sync pairs. Okay, so these are exactly the nodes that want to communicate with each other. So we can have 2 of these, 3 of these, however many you want. K is the number of such pairs. And what would we like to compute? We'd like to compute some protocol which allows us to send any possible messages we'd like to send from every source to their sync. Okay, so the way protocol works is as follows. Initially, each of the source nodes have a 1-bit message, xi. This is not determined by the protocol. This is an input to the protocol. And then the protocol will have nodes communicate over synchronous rounds with the objective of having all the syncs receive their designated message. So in each one of these rounds, each node is allowed to send a 1-bit message along each of its edges, and we'll take it 1 round to cross. So pictorially, on the example on the 3-unicast instance on the right, the way this might look is as follows. In round 1, we'll start shipping these messages along the shortest possible path from each source to its sync. In round 2, we'll keep doing the same. Now in round 3, we notice that we cannot send both the red and the blue message simultaneously along the same edge, leaving T3. So what we'll choose to do here in our protocol is to send maybe the red message and remember the blue message for later. Okay, by the end of round 3, the red message will have crossed this edge. And then in round 4, we can send the blue message along this edge. And finally, in round 5, all the syncs will have received their message. Okay, and this number 5 here is what we're going to try and minimize. So a little more generally, what we'd like to minimize is the maximum time until each of these syncs have received their designated message. Okay, hopefully all of that is clear. So now let me spend a moment talking about what such protocols might look like. So in the previous slides, what we saw was an example of a routing protocol where nodes store and forward their messages. Again, this is exactly what's done in the internet. These intermediary nodes are called routers for a reason. And really what's going on here, there's some kind of analogy to shipping physical commodities maybe along a road network, right? Instead of thinking of packets of information, we're thinking of packages of just a message, a letter sent by your mail person. But as it turns out, and as it might not be surprising to some of the people in the audience, this is not the right way to think about information dissemination in a network. So as Alsved et al. Showed in a highly influential work in the early 2000s, information is not a physical commodity, and there are more elaborate things we can do which can actually get us some gains, at least for some communication problems. So just to be a bit more clear, in general, a protocol can do more than just store and forward messages. It can send any function of the messages it received. Okay, so basically what I'm saying is that nodes in the network are allowed to encode and decode messages that they've received so far, and hence this talk appearing in this session. Okay, so these kind of more general protocols are referred to as network coding protocols. Pictorially, it might look something like this. So here we have some subnetwork, and in some round, nodes U and 1 might send a blue and a red message to V. In the next round, U3 might send a green message to V. And then in the next round, V might send any function of these 3 messages to its neighbor W. Okay, this could be one of these messages, as in routing protocols, or it could be, say, the max of these 3 bits, or it could be, say, the sum of these 2, and so on and so forth. Great. So we've allowed ourselves more flexibility in the design space of algorithms we're willing to accept, or protocols. And now the natural question is, does this buy us anything? Do we get some speedups from using network coding compared to just the kind of natural, naive solution, which is routing? And what I'm going to show you in the next slide is that the answer is yes, just like a small example to convince yourself of the fact. So here we're going to consider this following network, referred to in the literature as the butterfly network for obvious reasons. And what we're going to have here are 2 source sync pairs. And I'm going to convince you briefly that routing time for these for this 2 unicast instance is at least 4 rounds, whereas coding allows you to solve it in 3 rounds. Okay, so let's start by convincing ourselves that routing takes some time. So if you look at the blue pair, you'll notice that there's exactly 1 path of length less than 4 between the source and the sink. So if you want to route in less than 4 steps, this is where you need to route. The same is true for the red source sink pair. Now, unfortunately, if we try and route both of these simultaneously, what we find is that we run into our old familiar congestion bottleneck problem, which says that both red and blue messages want to use this edge at the same time. That's a non-starter. Okay, so either the blue message or the red message has to be sent along a longer path, or maybe wait for at least 1 round at node U. So routing-based solutions will take 4 steps. Okay, now what about coding? So notice that in 3 rounds, we can send the blue message to the red sink and vice versa. A priori, this seems useless, but bear with me. In addition, in 3 rounds, we can combine both of these messages at node U. As we know, red and blue make purple. And so in 3 rounds, we can have both sinks receive the sum of both messages. So putting both of these things, kind of doing both of these things in parallel, what we find is that in 3 rounds, both sinks receive the opposite colored message, as well as the sum of both messages. Subtracting one from the other, they get the message intended. Great. So what we see here is that the completion time coding gap, so the gain you can get from coding compared to routing, is at least 4/3. And so the natural question, which we address in this work, is how much faster can coding allow you to solve this problem? Is it always bounded by a constant? Does it grow with the problem parameters? And if so, how? So first, we show that indeed it can grow with the problem parameters, and we show that there exist k unicast instances whose completion time coding gap is at least polylogarithmic in k. So coding can speed things up by a super constant factor, at least some polylogarithmic term. On the other hand, we show that this is essentially tight. So polylogarithmic dependence is, is the best possible speed up you can get. As for any k unicast instance, this coding gap is at most log squared k. Okay, let me tell you a few things about some extensions, some other related work, and then I'll leave you some natural open questions. The kind of the objective of this talk was more than anything just to tell you about this problem and tell you that there's some interesting questions here. Okay, some extensions. So in this, in the toy examples we looked at in this work, we assumed unit capacity per edge. We can do general capacity. We assumed it takes a step to cross each edge. We can do general delay. We talked about minimizing the maximum completion time. We can talk about average time until all the messages get there. And we talked about single bit messages. You can talk about general messages. And for all of these extensions, we get essentially the same balance. Some polylogarithmic dependence on the problem parameters. So I haven't really talked too much about related work. So let me tell you a little bit about how these general message sizes relate to something that's been studied quite in depth, which is throughput maximization. So if you think about this for a second, throughput maximization corresponds to infinite sized messages. So for throughput maximization, there's a famous conjecture in the network coding literature, or maybe even networking in general, that the throughput coding gap is at most 1. And this conjecture has some surprising connections to other areas of theoretical computer science. In particular, if this conjecture is true, it implies optimal lower bounds for I/O-bounded algorithms, and actually gives tight lower bounds for integer multiplication, matching the recent breakthrough, which gives n log n time integer multiplication. On the other hand, the best upper bound we have for throughput coding gap follows from the long line of work on multi-commodity flow cut gaps, starting with Leighton Rao, and the best bound we have from there is logarithmic in K. So just to kind of convince you that there's some relations, at least between this special case of our problem to a lot of other areas in TCS. Okay, so let me wrap up with some natural open questions. So the first question, I think, kind of begs a solution, which is, what is a tight completion time coding gap? We know it can be at least polylog k. It's at most polylog k. What's the right polylog? Second question, so an attempt to get the optimal routing protocols has been studied quite in depth, starting with work of, at least as far back as the seminal work of Leighton Max Rao. And we know how to compute optimal or asymptotically optimal or constant approximation of the best routing protocols. So the natural question is, can we get the optimal coding protocol or some approximation thereof? And this, I think, is a good question for the audience here who like to think about encoding and decoding messages. Finally, kind of following up on the previous slide, as I said, the special case of infinite-sized messages, the special case of our problem with infinite-sized messages, has some deep connection with other areas of TCS. And the natural question is, does this work have similar connections? And as it turns out, the answer is yes. And in joint unpublished work with the same co-authors, we showed that using coding gap upper bounds from this work, we can get universally optimal distributed algorithms for a number of fundamental problems: minimum spanning tree, approx min-cut, single source shortest path, and so on and so forth. Whereby universally optimal, I mean, these algorithms are as fast as you could hope for any input graph. So rather than saying, you know, this runs in time t of n, here's some network where you need time t of n, some pathological network which might not be relevant to your problem, we get the right algorithms. So revisiting question number 3, are there other areas, are there connections with other areas of TCS? The answer is yes. So are there more such connections? All right, and with that, I think between the technical issues and whatnot, I'm a little over. So I'll thank you for your time and open the floor for questions.
Okay, so let's thank the speaker.
Well,
So we are a bit over, but I think we still have time for like 1 or 2 questions. So, could you go back a slide? There's something confusing me.
sure.
So you said that you get essentially the same bound for general message sizes, but then you have a conjecture which seems to conflict with that.
Oh, I see. Good. So the good. So the upper bounds are all the same. The lower bounds hold for the simple case of single message, etc., single bit messages, etc. Lower bounds, yes, of course, will not carry through because that would be a fantastic result. We don't know any result that gives a, you know, even a constant improvement for coding compared to routing for the throughput maximization problem.
Yeah, but we're of course routing for the conjecture to be true, like the easy one. Okay, so the question in the chat. So is there any difference between directed and undirected networks?
Yes. So directed networks, in some sense, the problem is a little boring. So it's not too hard to see that the coding gap for k sessions can be at most k. Just, you know, push along the shortest path for sourcing pair number 1. Then after you're done with that, do the same for number 2, and so on and so forth. And this is at most k times the length of the shortest path, which is a trivial lower bound. On the other hand, the butterfly network example I showed before, if you think about it a little bit, you can generalize this to a somewhat uglier network, but where you'll see a gap of k. So the problem for directed networks is unfortunately not particularly interesting, I guess.
Okay, and that's even in the for DAGs, let's say.
Actually, you know what? Let me take that back. I think there's a natural, interesting question here, which is, okay, so figuring out what the optimal gap, as I said, is somewhat simple. But then, if anything, there's even more motivation to design the optimal coding protocols, because that could give you potentially a speed up of a factor of k. Whereas for the undirected graphs, the speed up would be at most polylogarithmic. So there's definitely some questions, some interesting some interesting coding related questions there.
Yeah, any more questions? Yeah, if not, we're also a bit out of time. So let's thank the speaker again, and actually all the speakers in this session, so you can also clap. And if you want, then there's the beer sessions soon.